Hello everyone, welcome to my talk, Practicing the Art of Data Science. This is Jen Pei from Simon Fraser University, Canada. In this talk, I'd like to share with you some of the lessons and experience we learned from the data science research and practice. We all know data science is an interdisciplinary study combining science, engineering, and art. There is a joke. Whatever a principle we have to call it a science, it may not be really a science yet. So, in data science, we have to get information and skills from multiple disciplines. For example, from statistics, from machine learning, from data analytics. The core of data science is to connect those principles and apply the ideas and tools to solve practical problems involving a large amount of dynamic data in practice. Data science is focusing on various domains. Therefore, data science is really a pipeline starting from obtaining data. Scrub data, meaning cleaning data to a format that machine can understand and process, and then preprocess data, and using pattern mining techniques to find significant patterns from data. And also, we need to construct different models and make a prediction and forecast. Then, we need to put our models and findings into practice and find good understanding of the knowledge we can extract from the data and get the domain experts understand and adopt our findings. Therefore, data science, although we want it to stay as a principle, but indeed, in practice, it is always associated with some domain. And also, data science is a domain-oriented end-to-end solutions to interpret different kinds of data and transform data into interpretable knowledge. Data science, it is not a brand new discipline that will invent everywhere else. Instead, data science should be a strong connector and transformer to connect many general scientific principles and tools and make them available to the very first practice in practice. I was asked the question, what's the difference between data science and machine learning? This question was asked again and again. And I think one good answer was indeed from an article in the Harvard Business Review. In the article, what data scientists really do, according to 35 data scientists, the author said very well. The key skills for data scientists are not the abilities to build and use deep learning infrastructures. Instead, they are the abilities to learn on the fly and to communicate well in order to answer business questions, explaining complex results to non-technical stakeholders. As you can see here, the core role of data scientists are indeed connecting technology and users, and to interpret the technical solutions to domain experts. So communication, connection are the key features of data science. Let me use one example to show you how the connection, how the understandable domain knowledge are important for domain experts. Over 15 years ago, we did a paper we try to mine frequent orders from sequences. The idea is that we may find many sequential patterns, for example, from the bank service log. We can find different orders where customers may open their accounts, including checking account, money market account, retirement savings plan, mortgage account, broker account, and registered education savings plan, and so on. Then we said, well, instead of getting many accounts in sequences, which is the sequential patterns, thus, one thing we can do is that we can summarize multiple sequential patterns here as a partial order, which is an acyclic deck. Then you can see here, indeed, those partial orders will have quite good summarization capability over sequential patterns. We published a paper in the ICDM 2005 conference and got some citations, but not many. And we also wrote a full version of the paper published in the TKDE journal. And also we got the better citations, over 100. So this is a typical way of doing data science research from the algorithm point of view. We also show in our paper that there are some application scenarios. For example, we show the patterns found from bioinformatics datasets. However, our algorithm did not go into real application until we worked with software engineers, domain experts. Using the frequent partial order mining algorithm, we developed the end-to-end tool, a source code analyst tool. The tool can help us to analyze the patterns that programmers will use in constructing their codes. We published several papers on that. For example, MAPO is one tool we published in 2009. Essentially, we use the frequent partial order to mine and recommend the API usage patterns. As you can see, those papers published in the software engineering domain receive a lot of citations. The least one is 269 citations. The number of citations is not everything, is not the final goal, but it is a good indicator on how popular our methods are adopted. You can see here is that because we combined our method with domain practice, our algorithm has been used popularly by domain users. So from here, we can learn several things. First, data science should provide domain-oriented end-to-end solution instead of only developing algorithms or models. The end-to-end solution is very critical for data science algorithms. Without end-to-end solutions, it is very hard for data science algorithms to find good applications. Second, machine learning can produce good models. Data science can help people to obtain domain knowledge. And here, domain knowledge is the final goal in many applications. Therefore, data science is a broader umbrella including machine learning models. We can use machine learning models in data science, and combined with communication, visualization, interpretation to help the main users to get the knowledge. This is very, very important. Last, in data science applications, indeed, interpretability and understandability are the key. Only when the domain experts can understand and interpret the knowledge found using the machine learning or statistical models from data scientists can achieve their goals. So keep those 3 lessons in mind. They are important factors leading to the success of data science. Let me use one more example to illustrate why interpretation and understandability are so important. Let's consider how we can explain deep models. Many people tried different ways to understand deep models. For example, those methods can be categorized into 3 major groups. The first group is called the hidden neuron analysis methods. It tries to visualize, reword map, or label features that are learned by hidden neurons. However, one challenge here is that the qualitatively analyzing every neuron does not provide much actionable and quantitative interpretation about the underlying overall structure and mechanism of the whole model. The second approach is called model mimicking methods. Such a method imitates the classification function of a target model and builds a transparent model that is easy to interpret and has high accuracy. However, because we are mimicking the model we try to interpret, due to the reduction of the model complexity of a mimic model, there is no guarantee that a deep model with a large VC dimension can be comprehensively imitated by a simpler, shallow model such as decision tree. The third approach is called local interpretation methods. Such a method computes and visualizes the important features for an input instance by analyzing the predictions of its local perturbations. However, because we focus on local interpretation, therefore, perceptively, if we have 2 instances that are very close to each other, those 2 instances may not be explained consistently. That will create some issues for human understanding. Last year, Cynthia Rudin has one article analyzing the challenges in interpreting or explaining deep models. She said there are 4 major challenges. The first is that the explanations may not be faithful to the original deep models. Second, the explanations often do not make sense or do not provide enough details to understand what a black box model is doing. Moreover, a black box model is often not compatible with situations where information outside the database needs to be combined with a risk assessment. Last, black box models with explanations can lead to an overly complicated decision pathway ripe for human error. As a conclusion, Cynthia said, Stop explaining black box machine learning models for high-stake decisions and use interpretable models instead. Taking all those challenges in mind, we propose one general principle of deep model interpretation. That is, we need to provide exact and consistent interpretation of deep models. What do we mean by exact and consistent interpretation? We say a model M is an exact interpretation of a model N if M is mathematically equivalent to N. In other words, we do not mimic things. Instead, we want to have the interpretation mathematically equivalent to the target model. Second, a model M is a consistent interpretation of a model N if M provides similar interpretations for classification on similar instances. That is, if we have two instances that are sufficiently close to each other, then their interpretation should be sufficiently close to each other too. This is a key attribute that a good interpretation understandable by human being should have. Carrying these two requirements in mind, to build exact and consistent interpretation, we can transform a black box into a white box. In KDD 2018, we developed an exact and consistent interpretation of piecewise linear neural networks. The idea is that we conduct a piecewise linear neural networks here where the activation functions can be piecewise linear functions. Such activation functions are popularly used in deep models, such as max-out and ReLU. The key ideas in our approach is that we want a piecewise linear neural network mathematically equivalent to a set of local linear classifiers, such that a local linear classifier covers the instances within a convex polytope in the input space. We developed a tool called OpenBox, which is an exact interpretation of a piecewise linear neural network by an equivalent set of local linear classifiers in closed form. Each instance can be interpreted using the corresponding decision features. Let's look at the ideas a little bit deeper. We have a neural network where we have this neuron, and then this is the ReLU activation function. So it's piecewise linear, meaning the whole activation function is divided into multiple segments. Each segment is linear. Indeed, in general, we can apply these linear piecewise linear aggregation function to any of such kind. They can have an arbitrary number of segments. So we have a deep neural network. This is the input level. And then we have multiple levels of neurons. And then this is the output level. The idea here is that for each neuron, we can observe its response to an input case. That is, we have an input case here, and then this is, and for each neuron, it either being activated or not activated, and therefore it takes the state of either 0 or 1. We can form a convex vector like this. This is called the configuration of a piecewise linear neural network. For a fixed input instance x, which is a vector of x1, x2 until xd, we can collect the corresponding configuration vector. Then we can transform the problem into making a classification function on x following the linear classifier. Here, the tuple WB of fx identifies the decision boundary that exactly interprets the classification result of the input instance x. Now, how to find the consistent interpretation? What we can do is that we can try to find the polytopes where for any x and x prime, the configuration fx is the same as the configuration of x prime. So we can denote by P the set of n linear inequalities with respect to the vector of x. We have some observations. First, each configuration determines a polytope P. Each P defines a convex polytope. And all instances x in the same polytope share the same configuration and thus consistently share the same linear classifier fx. From there, we can get the conclusion is that interpreting the classification result of x by fx is exactly and consistent for all x in the same convex polytope. In other words, we can achieve the exact interpretation. You may be curious about what those polytope and the linear classifier may look like. Let me give you one concrete example. This is a training data set, which is a synthetic data set. This is the prediction result using a deep neural network. And this is the convex polytopes formed by our method. You can see each part here is a polytope. And this is the corresponding linear classifiers. And you can see here, we use the combination of linear classifiers to cut into convex polytopes to provide exact and consistent interpretation of the deep model on the original dataset. And we can show that the polytope here is mathematically equivalent to the original deep neural network. Indeed, we can compare our approach with the state of the art. So this is the comparison. As you can see, our method, the open box method, is more consistent than the existing state-of-the-art approach like the line. This year, we also put the exact and consistent interpretation of neural networks to cloud applications. In cloud application, one big challenge is that there's no access to model parameters or training data. To tackle the challenge, we have a few key ideas. First, we try to find the decision features for an instance to be interpreted by computing the closed form solutions to a set of overdetermined linear equation systems. We use a small set of sampled instances to construct the equation systems. Our approach indeed provides a strong theoretical guarantee. The exact decision features are identified with probability 1. Most recently, in the upcoming KDD 2020 conference, we have one paper to measure the complexity of deep neural networks with arbitrary activation functions. The major ideas are the following. First, we use a piecewise linear framework to approximate a given deep model with any curve activation function and guarantee approximation quality. Then, we can come up with an upper bound of the number of linear regions formed by such an approximation, and we use the upper bound to construct a complexity measure. Indeed, we can achieve interesting applications using the newly developed complexity measure. One important application is to get better understanding and control of overfitting. In the paper, we show that we can detect overfitting in the training of a new deep neural network, and we also can prevent overfitting by constraining model complexity. So, as you can see, in the previous talk, I show you that data science is much more than just developing new algorithms. Indeed, interpretability is very critical, and domain-oriented end-to-end solutions are highly valuable. The most important thing for data science is that we want to learn knowledge from data. Knowledge learning with data science is to turn black box models into white box models. Now, let me turn to the second half of my talk. Well, we know data science. We use a lot of data mining and machine learning techniques, and we have to design new algorithms. So one natural question is whether data science is to reinvent more wheels or data science is to assemble wheels to build more powerful vehicles. Let me use one example to illustrate. We work on graph mining for a long time. Indeed, graph is a popular data model. Graph is useful on two important aspects. First, graph is probably the last resort for the curse of complexity in real applications. In the applications of geographical networks, relationships, social networks, genomic networks, and so on. Whenever you have some data which is so difficult to handle, then probably you can turn to graph. That is probably the last thing you can try. Moreover, graph provides a very natural and nice divide and conquer approach in modeling, because in a graph, individual nodes and edges are well structured, but the global structures are weakly organized. Therefore, you can use the nodes and edges to represent those well-structured components of your data. And then you leave those not well-structured part into the global structure of the graph. Graph mining is amazing. First, we can have many different views on graphs. For example, you can look at the micro view, look at the nodes and edges. You can look at macro view the global structures and the properties. You can also look at the intermediate view, which are local structures and behavior. And you can also take into account the time, which is the temporal view. There are many important tasks in graph mining. You can do pattern mining, classification, prediction, clustering, outlier detection on graphs. But graph mining or graph computing in general is very challenging. Why? If we think about our whole idea in efficient data processing, indeed, we have some key assumptions. First, we assume that the data are well structured. And also, we assume that the data are well synchronized. However, in graphs and network data, all these two assumptions do not hold. Well, in graph and network data, we have some basic structures, but there are many unstructured elements. And moreover, the graph data are typically asynchronized. In my group, we conduct graph mining, graph computing for over 15 years. We do graph computing from data to intelligence. For example, our early work in 2004, we started to construct graph. We learn entities and relationships from the raw data and then extract the entities and relationships to form graphs. And then we also build graph database such as the storage engine and the indexing approach. We look at different applications of graph, for example, like geographical networks and social networks, and then we construct the specialized graph databases. On top of graphs databases, we conduct the different queries, provide query answering services, and we do the pattern mining. And also we do the information flow analysis, such as propagation and inference analysis. We work on privacy preservation on graph and network social networks. And of course, we work on machine learning over graphs, such as classification and clustering on graphs. So, let me show you some tasks we did in the last 15 years. First, we do graph classification in graphs. Indeed, this is an amazing task. If we want to classify, we can do different things. For example, we can classify nodes or edges. And we may even classify subgraphs. What information to use in classification? You can consider attributes of nodes and edges. You can take views of graphs. You can do the neighborhood patterns. Don't forget, you have one dimension which is challenging but also very interesting, which is time. Therefore, you can do dynamic graphs. We publish quite a few papers on graph classification. Those papers were published in good places, such as CIKM and ICDM. But, unfortunately, they are not very well cited. Meaning, people do not think those are important work. In addition to classification, we also work on clustering. We work on clustering in graphs and networks. Clustering in graphs and networks indeed is fantastic problems because there are many different ways to define clusters And each new definition of clusters will lead to new algorithm development opportunities. Moreover, on graphs and networks, the more information may be used, such as rich information in nodes. And again, we can of course work on clustering in dynamic graphs and to identify dynamic communities. For example, one paper we did in 2016 is called Fighting Gangs in War. The idea here is that we try to look for voters in election and find communities. A little bit different from the traditional social network communities, voter communities are very interesting. First, they should be similar to each other within each cluster, meaning they agree with each other. Second, they need to fight against each other among different clusters, meaning they strongly disagree with each other on different clusters. So this is a very interesting application. And we developed the algorithms and published the paper in KDD. Later, we also work on dynamic graphs. As I told you, it is a very interesting and challenging task. For example, in VLDB this year, we will publish a paper on density bursting subgraphs. We try to find the subgraphs such that the traffic will burst over time. Again, we published a series of papers in good places on the topic of graph and network clustering, such as VLDB, KDD, ICDE, and so on. But those papers were not cited very well. That means people do not think those studies are important. Why? By looking at our studies, our approach, and the user feedback, how the colleagues will talk about our work, we realize we should learn two important lessons. First, we develop many individual approach or specialized solutions. The way of one specialized solution for one particular problem is not scalable. It is not scalable for both academia and industry. For academia, because we present so many different algorithms and approaches, there are no general principles and methodologies. People don't really understand the general principles and methodologies behind our many algorithms. For industry, indeed, industry people are looking at many different problems. And instead of looking at the one approach in our method, they want general and adaptive solutions for many problems of the same or similar kind. Therefore, providing many new algorithms indeed do not address those concerns from both academia and industry. And moreover, data science should serve as the connector between problems in vertical applications and general solutions. There are already many off-the-shelf solutions, but we need to make them scalable in deployment. And also, we need to encapsulate the problem transformation into customizable units. Those are two important lessons we learned. And if we can overcome these two issues, we may make possible a larger impact. Indeed, we tried network embedding. we transform networks into vector data so that we can use general machine learning methods on graphs. To that extent, we do not develop any new machine learning or data mining methods. Instead, we try to transform the data so that the data can be used by many existing methods. Once we do the data transformation, we do the network embedding. Indeed, we have to make some decision. We have to make the trade-off. We can preserve some information, but at the same time, we have to sacrifice some information. Therefore, the challenge is what to preserve in network embedding. Indeed, there are many possible choices, such as transitivity and asymmetric transitivity, commodities, higher order proximity, and so on. And moreover, tuning the network embeddings is also challenging. So we have this AutoNE framework, which can help to automatically optimize the hyperparameters in making up network embeddings. The general idea of network embedding indeed is very simple. This is the general traditional graph and network representation. We represent a graph as a set of nodes connected by edges. Network embedding tries to transform such a representation into a vector space, such that each node becomes one point in the vector space. If two nodes are connecting by one edge, then the two nodes here should be close to each other in the vector space. After the transformation, indeed, we have sort of like a generative model of the graph. The embedding can help us to generate the corresponding original graph. We study different ways to preserve network properties in embeddings. For example, we have the asymmetric transitivity preserving embedding. The idea here is that we want to have a node serving as a source and the node serving as a target to have different roles, because in directed graph, the transitivities are in two different directions are different. And therefore, each node in the original dataset are mapped into two different vectors in the vector space. And also we look at different network structures. The microscopic structure, where the pairwise relationship or the similarity between nodes are preserved, and the mesoscopic structure, where the constraints are in a higher structural level. That is, the nodes in a commodity are more similar to each other. And we conduct a different embedding models for different structures. One challenge in making up network embeddings is that it needs training too. And indeed, there are many hyperparameters that need to be trained. Similar to the idea of AutoML, we developed a framework called AutoNE to help users to automatically tune the performance into embeddings. Using this idea, we developed the AutoNE approach, and this AutoNE approach applies the meta learning module to train the Gaussian process meta learner on the sample networks to distill the transferable meta knowledge about the optimal parameters configurations. Now, network embedding becomes a hot direction. Just as one example, indeed, Our several papers on the topic have been cited very well. Recall that in the previous slides, I showed you that our previous methods on classification and clustering, although published in top places, but they are not cited very well. The major reason is that those individual approaches solve narrow and specific problems, and people may have difficulty in applying those approaches. But network embeddings is such a general approach that now people all like to use them. We have many more ongoing work on network embedding and also understanding the complexity in deep models. As I show you, indeed, data science should serve as a connector. It should connect vertical application problems with general solutions. And data science is really to provide the frameworks, the methodologies, and the platforms. In summary, as I show you, we really learned from our research and practice in data science that data science need to provide domain-oriented end-to-end solutions. Interpretability is critical for human experts in different domains to obtain understandable knowledge. Data science practice is indeed highly related to specific domains, and data science should not just invent new views. More importantly, data science should be connectors and transformers. It should connect the data applications, the different domain practice with the general scientific principles and tools available already in many disciplines. Thank you. I'm happy to answer any questions.